In lesson 3.1, Extrema on an interval, we'll begin our study of the use of derivatives to accomplish something more than just saying, here's the derivative of a function. In lesson 3.1, we'll actually be using derivatives to find the maxes and mins of functions, particularly functions on a closed interval. The fact of the matter is this. If we have a function that's continuous on that closed interval, then certainly we need to be able to find a max or min. Now, that max or min might happen at the beginning or end of the interval. It might happen somewhere in between, but it will only happen where we have a critical number. So what we'll do here is we'll begin by presenting the extreme value theorem, after which we'll do an example, and then we'll talk about critical numbers and a procedure for finding these extrema, which will actually be a particularly easy procedure, so nothing to worry about here. There's only one thing that I can really, truly guarantee about this lesson. It will be extreme. Alright, so I changed my mind on the order of things. What we're learning here is in fact so extreme that we're going to begin with an example before we look at any of the theorems or notes or any of that stuff. So let's take a look at example A here. We're given the graph of this nasty looking function, negative 3x times the square root of quantity x plus 1. I've graphed it for you. Here it is. And what it wants us to do is to try to estimate the x value at which this function attains its maximum. Clearly its maximum is going to be right here, but what is the value of x at this point? In fact, what we're going to do is actually call that x value c. So I want you to go ahead and write down a value for c. It's simply your estimation. I hope it's negative. It should definitely be negative. Maybe negative half or negative 3/4. Not sure, but you take a guess. You write it down. And then what we want to do is differentiate this function. Plug in that value of c that you just estimated and see what the slope of the tangent line to this function is at the x value that you chose. So I'm not going to go through all the work. Of course, we would need a product rule here. There's a square root, so I should turn that perhaps into a x plus 1 to the 1/2 power. So I can rewrite it that way. Now I can do my product rule and all that good stuff. I certainly encourage you to pause this video and try doing it on your own. It is a good idea to simplify it once you get there and all that good stuff. But for the sake of time, I'm going to go ahead and work this out for you right now. If we differentiate this function, what we should end up with is negative 9x minus 6 divided by 2 times the square root of quantity x plus 1. So there is the derivative of this function. This will tell us the rate of change on this graph at any value of x that we want to put in. So what am I going to ask you to do now? Of course, I'm going to ask you to plug in the value of c that you chose and see what you get for the rate of change at that point. Well, if the rate of change is positive, then you chose a number that is to the left of the true max, because here the function is increasing. If you plugged in your value of c and got a negative, then you must have chosen a value that comes after the true value of c, because after c, this function appears to be decreasing or have a negative derivative. So what happens if you actually chose the right value of c? Well, I'm going to go ahead and tell you. The true value of c in this case is negative 2/3. And now that I've told you that, let's go ahead and plug in f prime of negative 2/3 and see what happens. Well, we work that through our calculator or do whatever you got to do, and we find that the derivative at negative 2/3 of this function is in fact 0. And that is conceptually very, very important. If the derivative were positive, the function would be increasing. That happened here. If the derivative were negative, that would mean the function were decreasing. And that would happen all along here. But at this value of c, right there in the middle, it's neither increasing nor decreasing, and it has a derivative of 0. And that is extremely important. And with that, let's go ahead and talk about the extreme value theorem, which will kind of formalize what we've done in this first example. Let's do it now. Alright, so the extreme value theorem, which we're going to use in our procedure for finding maxes and mins, is very, very simple, and I would argue very intuitive. It simply says that if we have a function, we'll call it f, and if f is continuous on a closed interval, which I'm going to call a comma b. Notice that the brackets are square. This is a closed interval. And if f is continuous on that interval, then f will have both a max and a min. Now, it doesn't tell us how many maxes and mins. It could just be one. Or in the case of a constant function, which is continuous, every point in the interval would be both a max and a min. So there's lots of derivations to this extreme value theorem, but all it's basically saying is if we have a continuous function in a closed interval, we should be able to find a max and a min. Not should. We absolutely will be able to. So let me tell you a little bit about how we're going to do this before we get into the procedure. If I have this closed interval, which I'm going to start at A and end at B, and on that closed interval I have some continuous function, what the extreme value theorem says is that we will have maxes and mins. In fact, it looks like our max might actually be at this endpoint, and it looks like our min would be down in this valley. Now this point right here is an interesting one. It's also a max of sorts. Because it's the highest point in its neighborhood, we call that a relative max, whereas this max over here is an absolute max. The function on that closed interval does not get any higher than an absolute max, nor does it get any lower than this, which is an absolute min. So how do we find these maxes and mins? Well, of course, we'll need to check the beginning and end points of the interval, but also we're going to have to look for critical numbers. Now, what are critical numbers? That's a very good question. A critical number is a number that we'll call C that meets one of two conditions. Either the derivative at that number equals 0, which is similar to what we saw in example A, or the derivative at that value does not exist. This could happen in the case of an absolute value function or a cusp or something along those lines. For example, there we go. Here you can see that the absolute min is at the beginning of the interval. We have a relative min at the end of the interval, but there are no critical numbers. Don't be confused. The slope here, the derivative of the function at this cusp, does not exist. The derivative from the left is positive. The derivative from the right is also positive. So never is the derivative 0 in between there. The derivative just fails to exist. However, that still counts as a critical number. So with that being said, let's run through a quick procedure, which I've just explained most of it to you, but a quick procedure on how to find Extrema on a closed interval. Alright, so the general procedure for finding Extrema on closed intervals, and I'm not going to use that sound effect anymore. I think that sound file is just about had it. But finding the extrema is actually a very easy process. The idea behind it is we're going to identify all possible candidates for extrema. Then we'll evaluate the original function at each one of those candidates. And from there, the highest evaluation will be the max, the lowest evaluation will be the min. It's that easy. So I do this in 4 steps. My first thing is I try to find all the critical numbers of f inside the interval a comma b. Now notice this is an open interval. Critical values are not going to exist on the endpoints of the interval necessarily, because I can only approach those from one direction. critical numbers I can approach from both directions. So that will find some of the candidates. In fact, that'll find all the candidates that are inside the interval. What I need to do is simply evaluate f for each critical number. Now, be very careful when you do this. You want to evaluate the original function, not the derivative. The derivative at each critical number will either be 0 or it won't exist. And we know that already because we found the critical numbers. So when you evaluate, you're evaluating the original function. We're trying to find the y value for each one of these x's. After we're done with that, and this is the step that most people miss, we need to evaluate f for each endpoint on the interval. And what I mean by that is we need to evaluate what f of a equals and what f of b equals, in addition to f of each critical number. Now, after we do this, we're going to have a list. It'll have at least 2 elements, being the endpoints, and then any critical numbers in between. And from that list, the lowest value is, of course, the min. And the highest value, which makes perfect sense, is going to be the max. And now, that's our procedure for finding these extrema. It's very easy. Identify all possible candidates, check each possible candidate, and then make your decision from there. Let me show you how easy it is with example B. At the conclusion of example B, I'm going to strongly encourage you to graph this function on your calculator and see for yourself if the results that we're about to find are in fact true. So if we want to find all the absolute and relative extrema of this function on the closed interval 0 to 4, our first step should be to find critical numbers. Now, how exactly do we find critical numbers again? Well, go back to the box right above the procedure. Critical numbers are where the derivative equals 0 or the derivative does not exist. So, if we want to find the derivative of this function, that should not be too difficult. I made this an easy polynomial for you. It's simply 3x squared minus 12. Now, to find those critical values, all I need to do is set my derivative equal to 0. And what I'll get are 2 critical numbers, x equals negative 2 and x equals positive 2. And before I even say it, you might have already caught what I'm about to say. X equals negative 2 is not even in the interval that we're concerned about. So while x equals negative 2 might be a max or min, it doesn't concern this problem because it's outside the bounds at which we're looking. So all we need to do now is simply evaluate 3 different values. We need to find f of 0, that is the beginning endpoint of our interval. We need to find f of 2, which is our critical number that we just found. And finally, we need to evaluate f of 4, which is the endpoint of our interval. So go ahead, run these through your calculator, do whatever you got to do. But remember, we're evaluating the original function here. We want to know the y value at these x values. We're not concerned about the rate of change. We want to know the y values. So f of 0, you plug that in. That's an easy one. That will just give us 0. F of 2, if you plug that in, you should get negative 16, while f of 4 gives you positive 16. So what does all this mean? What it means is that we certainly have a max, an absolute max, and that will occur at the point 4, 16. That is the highest of our 3 y values. Furthermore, it looks like we're going to have a min that occurs, and that will be at 2, negative 16. So what happens with this point 0, 0 then? It's certainly not an absolute max. It's certainly not an absolute min. And maybe what I should write here is absolute max, absolute min. But 0, 0 is something. If you just kind of observe this on your own, at f of 2, we're all the way down at negative 16. So to get back to 0, clearly we're rising up. And so what that must mean is that we have a relative max here at 0, 0. So we've identified all the absolute and relative extrema. We found the derivative, set it equal to 0. There was nowhere that the derivative didn't exist, so we didn't have to deal with that at least. But we had to evaluate f at both endpoints of the intervals and the critical number, which we did right there. The highest value was our absolute max. The lowest value was our absolute min. And then we just used a little bit of logic to figure out whether this other point was a relative min or relative max. So all that being done, let's take a look at one more example, example C, which will bring to light what happens when we have a critical value due to a derivative failing to exist. Let's take a look. So I forgot to re-encourage you to graph example B after we finish that example. So please pause this video right now, take just a few seconds, and graph that function in your calculator and see if those relative and absolute extrema that we found are in fact true. Alright, now let's move on to example C, where we're going to do essentially the same thing. This time we're operating with this function, h of t, and our interval is a little bit different from 3 to 5, but no big deal. We're actually going to do pretty much the same thing we did on the last example. We're going to begin by differentiating this, and of course I'm going to strongly encourage you to once again pause the video and try differentiating this on your own. If you do it correctly, what you should get is negative 2 divided by the quantity t minus 2 squared. Now, if we go ahead and set that derivative equal to 0, we won't get any critical numbers that way. So critical numbers, well, there's nowhere that the rate of change is 0. Not just on this interval, but at all. So are there any values at which t fails to exist? And here, certainly we can say yes, there are. When t equals 2, look what happens to this derivative. Exactly, we get a 0 on the bottom. So our critical numbers are going to be t equals 2, and that's going to be the only one. So let me go back to the original function. I need to evaluate it at the beginning of our interval, which is at 3. We need to evaluate it at all the critical numbers, which is 2. But wait a minute, 2 is not even in our interval to begin with. So we actually don't have to evaluate it at 2. It's irrelevant what happens there. And let's just evaluate it at the end point then of our interval. And if we do that, h of 3 will give us 3, while h of 5 gives us 5/3. And clearly what that tells us is that we have an absolute min, and that's going to happen at 5, 5/3. And we have an absolute max. And that absolute max will happen at the point 3, 3. Something does happen at t equals 2. Don't get me wrong, it's not in the interval, so it was no concern to this example, but something does happen at t equals 2. When you graph this function on your calculator and take a look, you'll see very clearly what happens at 2, if you couldn't tell just by looking at the function anyway. That is a critical number. However, even if it were in our interval, it would actually break the continuity of this function, and so the extreme value theorem would actually not apply if t equals 2 were included in the interval. We'll see some examples of those in the homework, so it'll make perfect sense. But with that, let's take a look at one last example. This is my favorite one because it's more conceptual in nature and easy. So let's take a look at example D. So why do I like example D so much? It's simply because everybody watching this video could get a different answer and all of us could be right, and that's beautiful. So what we need to do here is create a graph in this closed interval from -4 to 1 that has these 4 characteristics that I'm not going to read through because you can read through them yourself. However, by saying that it must be in the interval from -4 to 1, I'm going to go ahead and begin by simply blocking off that interval. That way I won't overextend my function and go places that I don't need to go. Now we are told that we have a absolute maximum at x equals -1. So I'm going to go ahead and draw the highest point that will be on my graph right there, where x equals -1. We're told we have an absolute minimum at x equals +1. So I will draw an absolute minimum. So everything that I draw on this graph will go no higher than this point and no lower than this point. That's how I'll make sure that this condition and this characteristic, rather, that's how I'll make sure both of those work. Now it does say I need to have a relative minimum at x equals -4, so I'll draw this a little bit down. But how can I ensure that this is a relative minimum? Well, that can only happen if the function begins by increasing. Of course, here I'll have kind of a hill, and here, well, this is the end of the interval, so it can be doing pretty much whatever it wants as long as it's going down at that point. Now we have this, well, now I've just covered this relative minimum. So we have this, this fourth characteristic that we need to cover. There needs to be a critical number at x equals -3. So right here, there has to be a critical number, but no extrema. How can we have a critical number but not have extrema? Well, if the derivative equals 0, does that necessarily mean that I must be on top or that I must be on bottom? Or could I have a horizontal tangent line but no extrema? And what I'm going to show you is actually, yes, that can happen. And in fact, I'm going to have it happen like this. Watch. I'm going to have this increasing, but here it's going to level out. So here I have a derivative of 0, but I'm going to keep my function increasing. So although it leveled out, it doesn't necessarily have to start going down. It can rise up, level out, and then keep rising up. And then afterwards, I'm just going to have my function drop so I can get to my absolute minimum at the end point. Now, your function might not look quite as beautiful as mine, or you might not have this rogue blue arrow hanging around, but either way, it should have similarities to this. This kind of thing, which we see quite often when we're dealing with the function y equals x cubed, this is a critical number, but it is not a max or min. Take a look. The tangent line is horizontal, but it is not a max or min. So, it basically goes like this. Not every critical number will give us extrema, but all extrema will occur at critical numbers. Well, unless we're dealing with a closed interval, of course, and then it can be on the ends. So, in this lesson, we've covered a few things. We started by talking about extrema, what they are, how to identify them. Essentially, they're just maxes or mins. And then we talked about how do we find these extrema. We said that we need to look for critical numbers. And we talked about how we do that. We simply differentiate the function, and we can do two things. Set the derivative equal to 0 and solve. Those will give us critical numbers. Or we could find where the derivative fails to exist. That would also give us critical numbers. Once we've done that, we also need to look at the endpoints of the interval, and that will help us identify all possible candidates for extrema. From there, we simply evaluate the function at all of these possible candidates. And once we have all those y values, then we can make our decisions about which ones are absolute maxes and mins and which ones are relative maxes and mins. So we've covered a lot of stuff. It'll all show up in your assignment, and so certainly I wish you a very extreme good luck.